Hello, this module covers fatigue theory and fatigue design provisions that are in the AASHTO specification. In the first segment, an introduction to fatigue theory will be presented, and then in the second segment, the details of the AASHTO fatigue provisions will be covered. A fatigue failure is a failure that occurs under a repeated loading that induces a cyclic stress, a stress that is well below the yield stress or buckling stress of the material. The first example of fatigue failures is probably the de Havilland Comet. I'll post a couple of links to YouTube videos about the comet near the link to this presentation. You should take some time to watch them. They're quite interesting. Basically, the Comet was the world's first production commercial jetliner, building off of jet engine technology from World War II. It was much faster than conventional propeller-driven aircraft, and because of that, it flew higher than conventional aircraft, and it was also the first to have a highly pressurized cabin. About a year after entering commercial service, though, the Comets began crashing without any obvious reason. Eventually, the Comets were grounded, and to try and figure out what was causing the crashes, they submerged the fuselage of one of the aircraft in a large tank of water. By varying the water pressure inside the fuselage relative to the pressure outside the fuselage, the researchers were able to simulate the load spectrum corresponding to pressurization and depressurization that the aircraft would experience during each flight, as it started off at ground level, ascended to cruising altitude, and then descended again to ground level. After some time, and after numerous pressurization cycles, a catastrophic crack appeared in the fuselage near one of the windows. Look at the shape of the windows in the Comet and compare them to a commercial jetliner. The square shape of the windows created concentrations in the stress in the fuselage that, when cycled, led to a fatigue fracture. Even though the stresses in the fuselage were certainly well below the yield strength or the tensile strength of the metal, cycling at these lower stress levels near a discontinuity led to a failure. Similar load spectra exist for other types of structures too. This slide shows the stress ranges on various components of an automobile. Note the nature of the load spectra for the suspension. It is fairly periodic in general, but there are spikes in the load, presumably where the car hits a pothole or a bump. These types of load spectra can be simulated in a laboratory by placing the vehicle on hydraulic actuators. In fact, our College of Engineering has the capability of doing this in the Rhodes Hall High Bay. This slide shows a load spectrum for a short span bridge over some period of time, maybe over the length of one day. Note that this is relatively variable in terms of the peak loads that are observed. That is one of the challenges of fatigue theory with respect to bridges. That is the high variability in loads that pass over the bridge on a day-to-day basis. It isn't very practical to test full bridges in a laboratory like the car 2 slides ago, but we can take components, called fatigue details, into our labs, and we can subject those to cyclic loads to simulate what they might be subjected to in a field environment. This slide shows a piece of bar stock with holes drilled in it or cut into it, and it was subjected to a cyclic fatigue type of loading until failure was observed. All right, to summarize where we are so far, a fatigue failure is a fracture under a repeated loading that induces stresses that are lower than the static strength of the metal, the yield strength or the buckling strength or the tensile strength. Fatigue fractures typically initiate at stress concentrations or stress risers within the members, like the hole in the plate on the right. But in theory, they can initiate at any discontinuity, including very, very small flaws that are inherent in the material itself. In structural engineering, we base our specifications on constant amplitude fatigue theory. Some definitions that are useful include S sub m, the mean stress or the average stress. The stress range, delta S, is the difference between the peak stresses, the difference between the maximum stress and the minimum stress. The alternating stress is basically half of the stress range. The stress ratio, R, is the ratio of the minimum stress to the maximum stress. And finally, the alternating ratio is the alternating stress divided by the mean stress. The equations on this slide are provided as a reinforcement for the graphic on the previous slide. Fatigue behavior is generally researched by subjecting a component or a member to a constant amplitude stress range and then counting the number of cycles that it takes to reach failure, which is usually defined as a fracture. If we create a chart with the stress range S plotted as a function of the number of cycles to failure, N, then each black dot represents one experiment. If you have enough experiments on the same detail at different stress ranges, then a curve can be plotted for that detail. These curves are called SN curves, and they are typically plotted on semi-log or log-log charts. SN data typically shows less variability at shorter lives and greater variability at longer lives. And the variability in data can range from less than a factor of 2 to 1 or 2 orders of magnitude. Most materials have a continuously sloping SN curve like the one shown here. Depending on the loads that are required and the stiffness of the components, the rate of loading can be anywhere from 2 seconds per cycle up to 5 cycles per second. Some components can sustain millions of cycles before failure, so constructing an SN curve can take a lot of time. If you were testing at 2 cycles per second, for example, it would take approximately 6 days to reach 1,000,000 cycles. And that's assuming that the system can operate 24 hours a day without having some sort of interruption. Moreover, multiple specimens are typically tested at each stress range to account for random variability. When enough data is available at several different stress levels, SN curves are typically drawn through the median lives and thus represent a 50% chance of survival. Under non-corrosive conditions, the SN curves for a few materials, most notably low and medium strength steels, contains a knee or a kink between 1 million and 10 million cycles, as is shown on the chart here. When subjected to stress ranges that are low enough, components made of these materials won't fail, regardless of how many cycles are subjected to, and they are said to have an infinite fatigue life. This infinite life typically isn't observed under corrosive conditions, but that generally isn't a concern for most bridges. Based on a 50% chance of survival, ASTM offers the following definitions. The fatigue life is defined as a number of cycles that a given specimen sustains before failure of a specified nature occurs, typically a fracture. The fatigue strength is defined as the stress range that corresponds to a failure for a given number of cycles, determined using an SN curve. And the fatigue limit is defined as the limiting value of the median fatigue strength as corresponding to an infinite life, which is sometimes referred to as the threshold stress range. The AASHTO and AISC fatigue provisions are based on a series of SN curves that represent a range of details that are cataloged. Each of these curves has a sloping portion that represents a finite fatigue life at a higher fatigue strength over a shorter fatigue life. And those are shown here. And then they each have a horizontal portion that represents an infinite fatigue threshold, where detail can theoretically survive an unlimited number of cycles as long as the stress range is low enough. Note that each one of these curves is labeled with a letter, A, B, C, D, or E, or in some cases a B prime, C prime, or E prime. There's still one problem to be resolved, however. Our fatigue theory is based on constant amplitude loading, but our structures see a variable amplitude loading in reality. Cumulative damage models are used to account for this discrepancy. Two of the most recognized models are Miner's rule and the inverse power law. Miner's rule, which is also known as the Palmgren-Miner linear damage hypothesis, dates back to the 1920s and the 1940s and provides a tool for relating our constant amplitude fatigue theory to the variable amplitude fatigue reality. Okay, hopefully by now you have a basic understanding of the theory of fatigue. So our next step would be to take a look at how it's addressed in the AASHTO specification. That will be the topic of part 2 of this module.